Hello everyone. So today we are going to learn about space complexity. So space complexity is order of growth of memory size or RAM space amount taken in terms of input size. So as you can see, it is very similar to time complexity, which is, as we know, order of growth of time taken in terms of input size. But here, instead of time taken, it's memory taken or RAM amount taken. Alright, now let's see few examples to understand better about space complexity. Alright, so let's see this function first. So in this function, we are returning the sum of first and natural numbers, and here we are using the direct formula. Alright, and I get, and I'm assuming you must be knowing about this formula. Alright, okay. So can you tell me the number of variables here? The number of variable is only one, n, right? And we can see that space complexity is order of growth in terms of input size. All right, so suppose if n is 100, then the number of variables would be still one, right? And suppose n is 1000, the number of variables would still be one. So number of variables is not depending on input size. So we can say that space taken by this function is constant. So we can write space complexity as theta 1, right? Okay, let me tell you that as long as number of variables are constant, okay, meaning it's not array or list of variables, then the space complexity would remain constant. Hence, you can see that space complexity here is theta of 1 or constant space taken. Alright, now let's come to this example, this function. So what this function is doing, it is also computing sum of first and natural numbers. But here we are adding numbers one by one in this function, alright, as you can see in this function, as this loop, alright. Now count the number of variables here first, alright. It is, n first variable, sum second variable, and I third variable. Now if I ask if we change n, suppose let's take n 3, then the number of variables would be 3. If n is suppose 100, the number of variables would still be 3 and some I. If n is 10,000, then the number of variables would still be 3. So we can see that number of variables is not depending on input size. So we can say that the size taken by this function is constant. So you can say space complexity of this function is theta 1 or constant space. Alright, as I told you before that if the number of variables are constant, irrespective of changing our input size, the space complexity would be constant. Alright, now let's come to this example. Alright, this is a very important example. So here what we are doing, we are having a function which takes parameters as an array and its size, array size. Alright. And then we find the sum of all the elements of array through this loop, and then we return the sum. Alright, simple function. Now tell me the number of variables here. So one variable n, one variable sum, and one variable I. Alright, three variables and one more important thing, number of elements present in this container, which is our array container. Right, this will also contain elements, so this will also like contain variables which will have elements of this container. All right, now suppose n is 100, then how many variables would be there? One variable, second variable, third variable, plus 100 more variables, the elements of our array. Right, if n is 1000, then elements would be what? 1 2 3 plus 1000 elements, because n is input size of array. So array would contain 1000 elements. So we can see that number of elements here are directly proportional to input size, which is our n. So we can say that space complexity here is theta of n, right? So this is how we calculate space complexity. I hope this gets clear to you. All right. Now let's talk about one more important term called auxiliary space. Auxiliary space is order of growth of extra space or temporary space in terms of input size. Alright. By extra space I mean the space created in memory other than input or output. Alright. So let's see this example. So here this is the same function as we saw before. It is, having parameter as array and size of it, and we are computing the sum of all the elements of array and returning the sum. All right. So we did see that space complexity here is what? Theta of n. All right. Now, if I ask you what would be the auxiliary space here? So what did we say about auxiliary space? That it is extra space created which is not related to input or output. All right. So as you can see in this function, it only takes this array as input, and no extra array is used for computation. The only auxiliary space here is the declaration or space taken by these variables, sum and I. All right. And if we change the size or if we change the input size, which I mean n, then still the number of variables would remain constant. Hence, auxiliary space would still be constant, which is theta of 1, right? So I hope this is clear to you that what is auxiliary space, right? Now, if I ask you like if we have to compare two functions to find the efficiency, then what would be the deciding criteria? So, a direct answer, it would be auxiliary space. Alright. Now, you might be wondering why. Alright. Now, let me tell you about it. Suppose if you talk about array problems, list problems, or any problems which use input containers, then they're going to use theta n space for input, right? For passing array into their parameter, like in this function, right? So space complexity would be theta n. So if suppose if I use an extra array here of suppose a, right, of size n, okay, so the time complexity array, the space complexity would still remain, theta n, right? Okay, let me tell you, what would be the space taken by this one? It would something be c1n, right? What would be the space taken by this one if there was this function? C2n. And then there are some variables which would take time something C3. So what would be the total space taken? C1n plus C2n plus C3. Right, so we can club C1 and C2 and we can say something C4. So it would be C4n, right, plus C3. Yes, and if we find the order of growth, what would it be? We'll ignore the lower order terms and we'll ignore the coefficient of leading term. So it would be n, right? So this is what I was talking about. If we add this, we'll still have the space complexity of theta of n. But what would change here? This. auxiliary space, right? Auxiliary space would change here. It will then become theta of n, right? So this is what I was talking about. We are, more concerned about auxiliary space or extra space taken by the function. All right. Okay, let me tell you about something about sorting algorithms, which will come later in this series. Suppose if we talk about sorting algorithms such as, bubble sort, quick sort, insertion sort, etc. What they do, they don't take any extra array to sort. Alright, so their auxiliary space would be theta of 1, right? But there are some sorting algorithms such as merge sort, which requires an extra array to compute the sorting. Alright, so its auxiliary space becomes theta of n. Now in all these sorting algorithms, we have to pass input array into the functions, right? Whether it be bubble sort, quick sort, or merge sort. So in every case, the space complexity would be theta of n. Alright. So what would be the deciding criteria? What would be the deciding criteria then? It would clearly be auxiliary space, because in sorting algorithms such as bubble sort, quick sort, we have, space complexity as theta n. But we have auxiliary space as theta of 1. And in sorting algorithms such as merge sort, we have space complexity as theta of n. But we also have auxiliary space as theta n. So we have to find the efficiency. Since the space complexity is same, we'll go to auxiliary space. So this is how we compare the efficiency of programs in terms of size they take. Alright. So this was all about the space complexity and auxiliary space. And this is the last video of asymptotic analysis. And from the next video, we'll start a new topic. And I'll end this lecture today.